Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And in this hour, we're going to throw the lines once again because this hour belongs to you. This is your hour. In fact, why do you simply sit there listening to the radio, watching the TV, acting passive like a couch potato? Why not be part of the fun? Why not give us a call at 866-323-2129? Let's say it's 4 o'clock in the morning, and there you are all alone, can't sleep, and something grabs you. You just got to talk to somebody because you have a brainstorm. But, hey, it's just you and the radio. So what are you going to do? You're going to give us a call at 866-323-2129. Or let's say you're having dinner with the kids, and the kids ask you a question that leaves you stumped. What are you going to do? Well, you're going to call 866-323-2129, and you're going to put them on the radio. Why not have their thoughts heard on over 100 radio stations that carry Science Fantastic? So why not put them on radio? So in other words, this hour is your hour. It's a time when you can ask the questions, no matter how dumb or silly they might seem. I mean, after all, when Isaac Newton asked himself a simple question when he was 23 years old, he asked himself a simple question: if an apple falls, does the moon also fall? And when he answered that question, he worked out what is called mechanics, otherwise known as physics. Everything we know about machines, everything we know about rockets, the laws of motion were worked out by Isaac Newton because he asked himself a simple question that even kids would ask: is the moon falling? And the answer is yes. Believe it or not, the moon is in free fall. It doesn't hit the Earth because, of course, the Earth is round and the moon goes around the Earth. But yes, the moon is in free fall, just like all the astronauts. Okay, well, let's move right along and take the next listener phone call.
Obviously, planets and stars are very far away. So my question comes to you as, would you say that the bigger problem to getting to the stars and planets comes from the sheer distance away from Earth that they are, or the fact that since they are so far away, that we just don't have enough fuel to get there in the first place?
Well, the answer to your question is actually yes for both. The reason why we cannot go to the stars anytime soon is because, A, they're very far away, and to get there requires an enormous amount of fuel. For example, let's take the Saturn rocket. The Saturn rocket went to the moon in 3 days, and it was the biggest rocket ever created by the human race. And if the rocket were to go to the stars, how long would it take? It would take the Saturn rocket 70,000 years. I repeat, about 70,000 years for it to just make it to the nearest stars. So obviously, chemical rockets are not the way to go. Chemical rockets are simply too feeble. No matter how powerful they may look on national television, blasting off from Cape Canaveral, they are puny compared to the enormous distances involved with the universe. So how are we going to get to the stars? Well, in my book, Physics of the Impossible, I lay out what the designs are for starships. One is to use fusion power. This is called the ramjet fusion engine. It's basically a gigantic ice cream cone in outer space. It scoops up hydrogen in the forward direction as it moves, burns it, fuses it in its chamber, and then spews out gas and exhaust on the other end. And so the fuel supply is limitless because it scoops up interstellar hydrogen, and there's basically an infinite amount of interstellar hydrogen out there. And so that's one way to do it, the ramjet fusion engine. The only problem is that we have not yet attained fusion on the planet Earth for peaceful purposes, let alone for star travel. The next possibility is antimatter rockets, just a la Star Trek. if you watch Star Trek, they always talk about impulse power from the antimatter engines. That sounds great. Antimatter gives you total conversion of matter into energy via Einstein's famous equation, E equals mc squared. So, what's the catch? There's always a catch someplace. The catch is antimatter, even though it does exist, is extremely expensive to make. The only way known of making antimatter on demand is with an atom smasher. And think about that. The atom smasher we have in Geneva, Switzerland, the Large Hadron Collider, is only a fraction of the energy necessary to go to the stars. In fact, it is a quadrillion times too small to create enough fuel to take us to the stars. Now, another proposal was highlighted by Stephen Hawking, my colleague, just a few months ago, and that is, why not use solar sails energized by laser beams to blast postage-size starships to the stars? Now, we've been brainwashed by Star Trek. We've been brainwashed into thinking that a starship has to be the size of a battleship, like the Enterprise. The Enterprise is huge on that TV program. Well, why not send a postage stamp chock full of computer technology, cameras, recorders, receivers, transmitters? Why not send a postage stamp, because of modern electronics we can do this, and put it on a sail. The sail is perhaps no more than the size of several feet, and then use laser beams on the Earth to shove these postage-size sails into outer space. That means you wouldn't have to have any rocket fuel. The rocket fuel, if any, is actually on the Earth in the form of what energizes the laser beams. And so with laser beams powerful enough, you can actually send these things out to Alpha Centauri at about a fifth of the speed of light. In about 5 years, think about it, you could reach Alpha Centauri, the nearest star. Now, you may say to yourself, hey, that's really neat. Why not send a postage stamp computer to the nearest stars? Well, what's the catch? There's always a catch someplace. And the catch here is that the laser beam necessary to energize this would have to have the energy of 100 megawatts of power. That's 100 nuclear power plants. So think of 100 nuclear power plants, all energized to shoot a laser beam to unfurl a sail in outer space that carries a postage stamp to the nearby satellites at a fifth of the speed of light. Well, each nuclear power plant, in turn, costs about, $2 to $5 billion, and you need 100 of them. So you very quickly see what the problem is. The problem is cost. We got to bring the cost down. In fact, much of the problems with building these starships is cost. Antimatter is very expensive. It costs a lot of money to build 100 nuclear power plants, and so we're not going to go to the stars anytime soon. However, I say perhaps in a century with the falling of prices, we may be able to send the first starship to the stars. Okay, well, moving right along, let's take the next listener phone call.
Hello, Professor Michio Kaku. This is Paul Smith from Vancouver, British Columbia, Canada. And my question is a concern I have regarding the Fukushima disaster. Now, I'm wondering if the fuel rods or the pellets have breached the containment vessels. Where is that fuel? Is it possible that it goes into the Earth, actually melting through layers of rock and maybe going right to the other side of the Earth? Do we know anything about this? And Building 4, if it's going to blow, is this not the worst environmental disaster the Earth has ever seen, far beyond Chernobyl? Look forward to hearing an answer from you. Thank you. Bye.
Well, just recently we passed the 5th year anniversary of that horrible nuclear power plant accident, and it was time to, think about the future of nuclear energy given the enormous problems caused by that accident. First of all, we know more or less the state of the reactor. We had 3 full-scale meltdowns. 3 full-scale meltdowns. In fact, the cores of all 3 actually liquefied. We've never seen this before. Even at Chernobyl, even at 3 Mile Island, we did not have a complete liquefaction of the cores, but that's actually what happened at Chernobyl. Now, what happens when the core goes through the Earth? Well, there is something called the China Syndrome. It's a movie, but it's also a slang in the nuclear business that if you have a meltdown, perhaps the hot core will melt right through the floor of the reactor, right through the bedrock of the Earth, right through the center of the Earth, and go all the way to China, and that's what's called the China Syndrome. Well, you're not going to get the China Syndrome. However, we do have computer simulations of full-scale meltdowns. They're called Class 9 simulations. We do know that you're not going to melt all the way to China. However, you will melt right through the bottom of the containment vessel onto the floor of the reactor. At that point, you will have a steam explosion capable of blowing the lid right off the reactor. And that's what happened at Chernobyl. Chernobyl, we had a steam explosion and a hydrogen gas explosion which blew the lid off the reactor. If you calculate the total amount of inventory that was released into the environment, roughly 20% of the core at Chernobyl was essentially vaporized and shot into the atmosphere, creating havoc in the area around Kiev. Now, it turns out that the Fukushima disaster did not release that much radiation into the atmosphere because a lot of it was still contained within the structure at Fukushima. However, we do not know the state of the core. The core is in liquefied form. It has since perhaps resolidified. Submarines have been sent into the bottom of the reactor to try to take photographs of the melted core. They were unsuccessful. So believe it or not, we are going blind. We do not yet know what the state of the core is. The accident is still in progress. Think about that. Just like Chernobyl. The Chernobyl accident is also in progress. How did the Russians stop this raging reactor fire back in 1986? Believe it or not, they did it with the Red Air Force. The Air Force was called in. They sandbagged the reactor by dumping borated sand and borated liquid on the burning reactor. They basically entombed it in concrete, and therefore the accident is still in progress.
This is Science Fantastic. You're listening to Science Fantastic with Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. Once again, the lines are open. This hour is your hour. This is the time when you can give us a call and get on national radio. Well, really briefly, where we last left off, we were talking about the Fukushima and Chernobyl disasters, which are still going on. Even though that Chernobyl accident took place so many years ago, it turns out the core has been sandbagged, entombed in concrete, but it is still melting. Not the China, but it is still melting right through the floor of the reactor, and we still do not have a permanent way to stop the core from continuing to melt into the Earth. One possibility is to dig a tunnel underneath the Chernobyl accident, and then reinforce it by creating a pan underneath the core to prevent the core from melting any further into the Earth. At Fukushima, we have a situation where we have 3 melted cores that are continuing to melt, and we don't even know what the configuration looks like. In fact, the Fukushima disaster is still not under control at all. Robots have been sent in because it's too radioactive for ordinary workers to work more than just a few minutes, and each time the robots have failed to carry out their primary missions of bringing the accident under control. And so the short story is, both accidents are still in progress. They have to be monitored very carefully because who knows, maybe another steam explosion could rip the reactor apart and the accident starts all over again. Stay tuned. Okay, well, moving right along, let's take the next listener phone call.
Stephen Hawking recently elaborated on his previous ideas
that black holes can remove information from the universe. What does Stephen Hawking mean when he says that black holes are removing information from the universe?
Okay, well, you ask a question which is at the cutting edge of modern physics. In fact, if you can find the answer to this problem, you may win the Nobel Prize in physics. Well, everybody knows, even children know, that when something goes into a black hole, it doesn't come back out again. In other words, a black hole is a cosmic roach motel. Everything checks in, nothing checks out. Now, if you have the Encyclopedia Britannica and you throw the Britannica into the black hole, it's lost forever. The Britannica never comes out again. But you see, there's a problem there, because that violates quantum mechanics, which we think is the ultimate law of the atom and atomic physics. In quantum mechanics, it turns out that information is never lost. Now, you may say to yourself, now, wait a minute. If I burn the Britannica, isn't the information of the Britannica lost, even under ordinary chemistry, when I burn it? And the answer is no, because in principle, you can move all the molecules backwards in time, run the videotape backwards, and so all the fumes and the flames disappear, and you get back the Encyclopedia Britannica. Now, of course, to do that would stretch the imagination. But in principle, because that's what quantum mechanics says, in principle, it is possible to hit the reverse button and have the Britannica unburn and reform as the Encyclopedia Britannica. Now, black holes are different because you can't run the videotape backwards because nothing comes out of a black hole. And so the thinking was, as Stephen Hawking said, black holes must violate quantum mechanics. Information is lost forever. Well, I work on something called string theory, which is a quantum mechanical theory, but it also embraces all of Einstein's theory. In fact, we think it is the theory of everything. It contains both atomic physics, the theory of the atom, as well as relativity, the theory of the universe itself. And quantum mechanics says that information is never lost. In principle, you can always run the videotape backwards. But if nothing can get out of a black hole, where did the radiation go? Where did the information come from? Well, you see, black holes are not entirely black. It was Hawking himself who said that black holes are actually gray. They seep out tiny quantities of radiation, and that's where we think the information is. If you could retrace all the photons coming out of a black hole, which we cannot do in practice, we can recreate the Encyclopedia Britannica. So Hawking admitted defeat. String theory, score 1 for string theory, score 0 for Stephen Hawking on this question. Okay, well, let's take a short commercial break, and after the break, we're going to continue with Science Fantastic.
You're listening to Science Fantastic. Here's Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. Okay, well, let's move right along and take the next listener phone call.
Hi, Dr. Kaku. This is Brendan. I was just calling to get a little insight on what the big crunch is and what might happen in that scenario and what might happen after that. All right, thank you for your time.
Well, many years ago when I was first learning about cosmology, I learned that according to Einstein, there were 3 possible futures for the distant universe. One possibility is that after the Big Bang, the universe just keeps on expanding and gets colder and colder, and that's called the Big Freeze. The Big Freeze is when the universe, it just keeps on expanding, doesn't stop at all, and it gets colder and colder, and will all basically freeze to death. That's the Big Freeze. The other possibility was the expansion of the universe could stop and reverse itself. And then the distant galaxies would come closer and closer to the planet Earth. And instead of getting colder, it would get hotter. The galaxies would come closer to the Earth. And when you look at the night sky would become totally white because of all the stars and galaxies that are rushing toward the Earth. In fact, it would get so hot that perhaps there could be another explosion, and perhaps we would get what is called the cyclic or oscillating universe. And the third possibility is that we're somewhere in between the two, but it would still last forever, the expansion. Well, now we have satellite data, and we now have proof that the universe is not only expanding, but it is accelerating. We once thought that the universe was slowing down, but no, it's actually accelerating. So at the present time, the leading possibility for the future of the universe is the big freeze rather than the big crunch. But we don't know why it's happening. There's something we think called dark energy. We're not positive, but something we think that's called dark energy that is pushing the galaxies apart, giving us the expanding universe. But if it's pushing all the galaxies apart, then what is it? Well, according to Einstein's theory, it is the energy of nothing. Even nothingness has energy associated with it. But how much nothingness and how much energy is there in the universe? We don't know. Now, string theory actually does explain this, the accelerating universe, but cannot give you a prediction for the amount of acceleration. So at the present time, we really don't know what's causing the accelerating universe. If you ever find out, you'll win the Nobel Prize in Physics.
There may be an infinite number of universes, but there's only one correct answer. This is Science Fantastic. You're listening to Science Fantastic with Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. Once again, you are listening to Science Fantastic, and it's open mic in this hour. Okay, well, moving right along, let's take the next listener phone call.
Hi. My question is, in this day and age, why are scientists still so apprehensive to look into the possibility of alien life?
Well, I'll be blunt. Many of my colleagues suffer from something called the giggle factor. And that is, anytime you mention UFOs or Bigfoot or Loch Ness Monster or whatever, they giggle. Their eyes rolled up into the heavens, and they sort of chuckle and laugh. Well, I don't laugh because that's not a very scientific approach to the question. However, there are legitimate concerns about whether or not alien life can exist in outer space. First of all, let me say that my own personal point of view. My own personal point of view is that, yes, they are out there. We can debate, however, as to whether or not they've actually landed on the Earth or can go between these cosmic distances between stars. But, yeah, I think there's so many galaxies out there, so many stars, and so many planets that we've identified that are Earth-like. We've taken a census of the Milky Way galaxy with the Kepler satellite. We think that perhaps roughly 1/10 or perhaps 1/20th of the stars out there seem to have planets going around them that could harbor life. In fact, the latest number that I've seen in the literature is about 1 billion. About 1 billion Earth-like planets in our own backyard. And to assume that we're the only game in town, I think, is a little bit presumptuous. However, to be fair, the critics of this theory would say that, well, there's a problem, and that is the distance between stars is so great that we don't think that they're going to reach us anytime soon. Well, yeah, it would take about 70,000 years for a Saturn V rocket to reach the Earth, but that assumes that they're going to use Saturn V fuels, that is, chemical rockets. I mean, after all, if they're not 100, but if they're 1,000, if they're 10,000, 1,000,000 years ahead of us, then whole new laws of physics begin to open up for them that we can only dream about at the present time. So in other words, the critics are right that with technology maybe 100 years more advanced than ours, we're simply not going to see aliens darting across the night sky. However, if aliens are perhaps millennia ahead of us, then there is a possibility. And we physicists actually rank extraterrestrial civilizations rather than talk about aliens in outer space. We actually rank them into type 1, type 2, type 3. A type 1 alien civilization would have the power of an entire planet. They would be planetary. They would, for example, control the weather. They would have enormous amounts of energy because they have the resources of an entire planet, sort of like Buck Rogers or Flash Gordon. Then there's type 2. They have stellar energy, the energy of an entire star. They play with stars like Star Trek. The Federation of Planets would be a typical type 2 civilization. And then there's type 3, galactic. They roam the galactic space lanes. They play with black holes. And that's type 3, like the Empire of The Empire Strikes Back. So you see, on this cosmic scale, you see that we are type 0. And of course, a type 0 civilization like ours is not going to be able to go into the stars. And of course, a civilization that's only 100 years ahead of us will also not be able to reach the stars. But if you are a full-blown type 1 civilization, you could be hundreds of years more advanced than us. A type 2 civilization would be a few thousand years ahead. Type 3 would be perhaps 100,000 to 1,000,000 years ahead of us. And on that time scale, you have to open your mind to the possibility of new laws of physics opening up to aliens from outer space.
Yes, Professor Kaku can help you with your homework. He can even help you with your kids' homework. But only if you ask. You're listening to Science Fantastic with Professor Michio Kaku. Here is Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. Let's take the next listener phone call.
I don't understand why we focus so much on expanding our horizons into the universe. I think that we should actually focus on expanding our horizons within our own life and the atoms and the molecules. Why hasn't anybody discovered something within molecules that we don't currently know? Let's not build telescopes to look toward the skies. Let's build telescopes, microscopes, to look towards the atoms. Why haven't we done that?
Well, the simple answer is that we have done it on a limited scale. First of all, we have electron microscopes where we use electrons. Electrons vibrate according to quantum mechanics, and as a consequence of the vibration, they can be used just like optics, just like photons vibrate, and we can use the vibration of photons to see objects in space. We can use the vibration of electrons, and the electron wavelength could be much smaller, and so we can actually see things on a much smaller scale than we can with a ordinary microscope. Well, if that's true, then why not use more subatomic particles to get even smaller? Well, you can, and they're called particle accelerators. So we actually do have instruments that can peer into the very heart of an atom, and these are the particle accelerators. So they, in turn, can reach down to distances much smaller than a proton. About a fraction of the size of a proton is the distance that we can probe with our atom smashers. The largest atom smasher is in Switzerland. It is the Large Hadron Collider. It found, for example, the Higgs boson just last year. And we think that there are more subatomic particles that we hope to find. So, yes, there is something like a telescope that can see even smaller than a proton, and that is particle accelerators. However, of course, to be fair, you're not going to get those fantastic pictures that we do get with optical telescopes and with electron microscopes. When you peer down at that scale, ordinary pictures become impossible. However, you can detect the presence of particles at that small distance, but you're not going to get glorious photographs of the inside of the atom. And that's because at that distance, everything obeys the Heisenberg uncertainty principle. Everything becomes fuzzy at these distances, and so you're not going to get glorious photographs. But you will be able to detect the presence of subatomic particles like the God particle, otherwise known as the Higgs boson. That we can do. Okay, well, let's take the next listener phone call.
Hi, my name is Corey Ross Robertson. So I am wondering regarding colonizing the universe. So I'm familiar with the Drake equation. I know one of the variables in the Drake equation is the likelihood that a civilization will survive long enough to allow for the civilization to develop enough to colonize other planets and utilize space travel. Given our planet's history and our civilization's history, what do you think the likelihood is of our civilization being able to overcome our destructive ways in order to last long enough to colonize other planets like Mars and even further outside of our solar system? Thank you. Have a nice day. Bye.
Okay, well, you asked several questions in one, so let's try to break them down to their components. First of all, you mentioned the Drake equation. Frank Drake was an astronomer back in the 50s who tried to estimate the number of intelligent civilizations there are in the galaxy. And the equation he came up with is not unreasonable, and we still use it today. First, you start with the total number of stars in the galaxy. We know that number. It's about 100 billion stars in the galaxy. And then you reduce that systematically. You reduce them, first of all, to the stars that are like our sun. So maybe half the stars in the galaxy are somewhat similar to our sun. And then a fraction of them have planets going around them. A fraction of those planets have liquid oceans and are potentially habitable. A fraction of them may have microbial life. A fraction of them may even have large, complex life forms. A fraction of them may even have intelligent civilizations. And the last factor in the equation is a certain fraction of these civilizations are long-lived. So they live long enough for us to detect them. In other words, they're not a flash in the pan. They're not going to simply blossom and then blow themselves up with nuclear weapons or biogerms or what have you. They're going to live long enough for us to detect their presence. Now, as you can see, there are a lot of variables in this Drake equation. However, now we have the Kepler satellite. We can actually answer many of the parts of the Drake equation. And the revised Drake equation that we now have because of the Kepler satellite, which can detect planets in outer space, is that perhaps a billion planets orbit stars that are Earth-like. And, however, there are still unknowns of the billion planets that are Earth-like. We still don't know what fraction of them have oceans, what fraction of them have microbial life, what fraction of them have intelligent life. But we're beginning to fill those gaps. However, you ask yet another question. And that last question is, of these civilizations that emerge from the swamp, how many of them don't blow themselves up? And, of course, that is a big question for which we do not have an answer. Let me say that however, we are on the brink of mastering weaponry, technology that can easily wipe out all life on Earth. And so it's not clear at all. It's not clear at all whether we will be able to tame these cosmic forces or whether these forces will blow ourselves up. Maybe when we go to the stars and visit planets, maybe we'll visit planets that are lifeless, that had a runaway greenhouse effect, that have radioactive atmospheres because of a nuclear war. We simply don't know the last factor in the Drake equation, and that is, are we nothing but a flash in the pan, or will we commit cosmic suicide?
You're listening to Science Fantastic. Now, Science Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And in this hour, we're going to talk about colonizing the universe. Not just colonizing the moon or colonizing Mars. We're talking about going into the universe itself. And with us today to separate science from science fiction is Professor Chris Empey, distinguished professor at the University of Arizona in Tucson, author of a new book, Beyond Our Future in Space. What it would be like to colonize Mars? What about going beyond Mars to the asteroid belt and Jupiter and Saturn? What about going beyond Saturn and going all the way out to the nearby stars? And perhaps even going through the galaxy itself. Once again, Professor Empey is an astronomer, not a science fiction writer, and we're going to talk about the science of colonizing the solar system and colonizing the universe. We should also mention that the reception we got with him is a little bit degraded. He's in Rome right now, speaking at the Vatican Observatory. That's right, the Catholic Church has an observatory, is very serious about the Big Bang Theory and the latest developments in astronomy, and he's actually at the Vatican Observatory where we caught up with him in Rome. First of all, NASA has said that, yes, Mars is it. The next target is not the moon, though of course we'll be going to the moon, but the next target is Mars. We hope to go to Mars somewhere in the 2030s, perhaps 25 plus years from now. But what's beyond Mars? What about going to Jupiter and Saturn and the asteroid belt? Some billionaires have said that perhaps we should begin the process of mining the asteroid belt. And perhaps life may exist on moons. Moons of Jupiter and Saturn that have liquid oceans heated up by volcanic forces. Forget sunlight. We're talking about moons that are in a frozen environment heated up by volcanic tidal forces, meaning they have liquid oceans, perhaps even room temperature. Perhaps you might even be able to take a swim in the oceans of the moons of Jupiter and Saturn, over 1 billion miles away from our sun. And then what lurks beyond that? What about going to the nearby stars? Stephen Hawking once again made headlines by advertising the first starship, not like the Enterprise, but the size of a postage stamp, driven by laser beams. Science Fantastic with Professor Michio Kaku. In this hour, we're going to talk about the potential of reaching out to the planets and eventually the stars. This is something straight out of science fiction, but it has seized the imagination of professional astronomers and astrophysicists. And the question is, can we begin the process of colonizing, well, the universe? With us today is Professor Chris MP. He's a distinguished professor of astronomy at the University of Arizona. He's the author of an exciting new book, which I highly recommend. The book is called Beyond, Our Future in Space. And we should also point out that he's written a number of books, including How It Began and How It Ends. So, Chris, glad you could be on Science Fantastic.
Yeah, it's great to be here, Michio.
Okay, first question for you is, how did you as a youth first get interested in science?
Well, as an astronomer, there's usually two ways in. One is, you have a little telescope and you just trade it out for bigger and bigger telescopes. But I lived in a cloudy place. I grew up in Britain, although my accent doesn't show it. The other way is through physics, and so I got in as an undergrad in physics, thinking astronomy was sort of the Wild West of physics, so that drew me in.
Okay. Well, let's just jump right into some of the substance of your book. First of all, you've probably been asked this question a million times. Why should we explore outer space anyway? Because it's expensive. It costs about $10,000 to put a pound of anything just in near-Earth orbit. That's a lot of money. We have so many problems on the Earth. So why explore outer space?
There are several reasons. I mean, the cost it's true, and we have problems on Earth. It's true, and we're not really built to survive in space. That's also true. But I think we're sort of genetically built to do it. We're explorers. I comment in the book on this DRD2, a variant of a single gene that's associated with migratory behavior of early humans, and it's correlated with risk-taking behavior in modern humans. We have a high incidence of this gene, and it seems to be that it's built into us to do the exploration that's not required for survival. We're just doing it out of curiosity.
And I remember as a child watching President Johnson on television. The TIROS weather satellite just went into orbit. People thought it was a waste of money to have a weather satellite out there, but it detected for the first time in world history a hurricane, a gigantic hurricane headed toward Texas, and they were able to alert the people, get evacuations going. People could hunker down and protect their property. And I'll never forget, that night, LBJ came on TV and said, tonight, the space program has paid for itself. And you know something? He was right. Well, let's just jump right into the content of your book. Let's talk about the moon and, of course, Mars. Mars is the target that NASA has fixed on. 2030, they say, could be the earliest that we go to Mars. So first of all, tell us how difficult it is to go to Mars, and what would it be like to actually land on Mars?
Well, for people, it's hard. We've been to the moon, although not for almost 2 generations now. And it's, 50 to 80 times further away, and therefore that much more difficult. It's a lot of exposure to radiation for the humans who would spend 2 years in space, more or less. And once you get there, you're very far from help, and so you're going to have to survive with what's available. And actually, that's the second reason I think exploring space is sort of inverting the argument that we don't belong there, to say that when we learn how to live on a place like Mars, it'll teach us how to live more parsimoniously on the Earth, because we'd have to mine the Martian soil to get oxygen to breathe, to get water to drink, and we'd have to be self-contained, and that's sort of how it'll have to happen. But that's hard, and that's why it's going to take 20 years.
And you've probably seen the movie The Martian, starring Matt Damon, and movies like that. What are your thoughts about Hollywood and whether or not they got it right with movies like The Martian?
Sure. I generally try to give Hollywood a pass on doing science in the movies, just because it's better to have science in the movies than to have some, bogus ideas being presented as science. The Martian got it mostly right. They got a pass on the Martian storms that sort of set up the whole story, because they just wouldn't have been fierce enough to do that damage. But in general, it's pretty accurate, and it certainly gave a sense of how, to struggle against that planet to survive and feed yourself, you'd have to be, working on all cylinders.
Okay, and let's take it now one by one. To go to the moon, well, it only took about 2 to 3 days to go to the moon. To go to Mars would take about a year to go to Mars, another year to come back. That's like 2 years. Plus, you're going to be staying on Mars for several months. And some people think that that's stretching it. The world's record for being in outer space for a human is a little over a year, set by the Russians. So do you think we're up to it? Do you think that we can really do it? That is a 2-year mission to Mars?
I think we can. Of course, the little ugly truth is that there are one-way missions to Mars. Mars One, the Dutch private venture, is a one-way trip. And actually, NASA was sort of outed on having, as a backup plan that's cheaper, of course, a one-way trip to Mars. And you'd be able to find people who are willing to go there and die there. Elon Musk has said he wants to die on Mars. So if you want to save money, you do a one-way trip. But I think there'll be people willing to take the risk of the 2-year trip and all that radiation exposure and the risk of really a catastrophe. There's going to be significant odds that you don't come back if you go to Mars, and you're one of the first.
Okay, and you mentioned Elon Musk, who is the billionaire behind Tesla Motors and behind SpaceX and PayPal. He was also quoted in the press. He subsequently had to clarify it, but he said that we have the possibility of nuking Mars, that is, dropping hydrogen bombs on the polar ice caps to melt them to begin the process of turning Mars into a habitable planet. What are your thoughts, therefore, about terraforming Mars?
Yeah, Musk is nothing if not ambitious. And so what he was alluding to is that if you want to terraform Mars, you basically have to kickstart a greenhouse effect. And the way you have to do that is to very quickly liberate a lot of the frozen carbon dioxide from the polar regions. And the way to do that, is by nuking it. That's probably not a way that the U.S. government would approve of. In fact, NASA's taken a very cautious approach to Mars. The missions that we send there sort of clean up after themselves. We try very hard not to contaminate the planet. So NASA's approach is pretty far from what Elon Musk is talking about. But even with Musk's concept, terraforming is a huge endeavor. Most studies that I've seen cost it out at something of order $1 trillion, and it's going to take generations, a couple hundred years to do the full terraforming of Mars. It's a fantastic endeavor.
Well, we had Dr. Robert Zubrin on our airwaves, and he said the following, that if you could raise the surface temperature of Mars just by a few degrees, which of course is an enormous task, then you begin to melt some of the carbon dioxide and ice, and they generate greenhouse gases, which then raise the temperature even more. So you have to reach a certain point, a point, and then you have the runaway greenhouse effect take place. Well, what are your thoughts? Is this simply science fiction, or what are your thoughts about the idea that if you could raise the temperature just for about a few degrees on the surface of Mars, it would set off a chain reaction of events, and it would basically be self-generating?
I think that is correct, and that's pretty much the kind of argument Musk is making. He's thinking of the fastest way to kick off that feedback loop and the greenhouse effect. So that definitely, you can do that. The trouble is full terraforming of Mars is a three-step process where that's just the first step. The second step would be to seed microbes on Mars to generate oxygen to be part of an atmosphere you could breathe. And you'd also need to add a buffer gas like nitrogen as we have on the Earth, and there'd be another mechanism for that with a different set of microbes. And only then could you start to develop a full biosphere. So this three-stage process is really what would take centuries.
Okay, well, some people say, well, the pioneers did it by living off the land. They came from England and from Europe, and they landed on our shores. They didn't bring that much luggage with them. They farmed. They were able to shoot animals. But on Mars, well, there are no animals. There's no soil, and it's frozen solid. And so what are your thoughts about living off the land? For example, melting the ice and separating out the hydrogen and oxygen from water to create breathable oxygen and rocket fuel. So what are your thoughts about living off the land?
Absolutely. That's certainly doable, and the Martian had that as part of the premise, too. So if we give up the idea of turning the whole planet into a place we could live, and we live in sort of protected bubble domes, then absolutely. There's machines. This is pretty simple chemical physics to take Martian soil. Basically, a ton of Martian soil is like a cubic meter, gives you about a liter of water. That's pretty impressive. So there's your water. You can chemically separate it, hydrogen and oxygen, and the oxygen you can breathe or you can use to make rocket fuel. So those the three basic ingredients you'll need to survive, as well as making soil and growing food hydroponically. Yes, all those technologies are really well understood and have been for decades. It's just a matter of putting enough infrastructure on the Martian surface to get it going, which is going to cost $100 or $200 billion.
Yeah, it's a lot of money. Now, some people say that, well, maybe liquid water actually flows on the surface of Mars. We've seen tantalizing photographs from outer space, from the orbiter, indicating that, well, perhaps there are remnants of water flows, liquid water flows on Mars. What are your thoughts? Is that putting too much into what could be an optical illusion?
I might have said that some years ago, but the evidence has just been piling up over the years, and I, across the street from where I work in astronomy, is the Planetary Science Department, and they're experts on this. And the evidence is just really compelling now. And there are actually situations, such as with the Phoenix Lander near the poles, or in some of the more recent photography, that show that when the water is briny enough, when it has enough salt deposits dissolved in it, it can be liquid momentarily, even on the surface now. So there's tons of water there. So in fact, if you took all the subsurface ice, water ice, not carbon dioxide ice, and melted it, it would cover Mars with about 5 centimeters of water, the whole planet. So there's actually quite a lot of water there if you could just liberate it.
Now, some diehards still insist that microbial life could live on Mars. They say that, well, look at the polar ice caps. We have yet to explore the polar ice caps. Or what about underground, into the permafrost? Perhaps there could be hot springs, volcanically heated water, streams underneath the ground. So what are your thoughts to the holdouts who still think there could be microbial life on Mars, except in more exotic locations?
Oh, I think they have a good argument, and the argument is based on life on Earth. So the extremophiles, as they're called, the microbes that sort of push the physical envelope of life on the Earth, are amazing. They live inside rock with no available sunlight. They live in pHs all the way from battery acid to drain cleaning fluid. They live at high pressure and low pressure, above the boiling point of water and below the freezing point. Incredible diversity of microbes on the Earth. And that diversity includes environments that we know exist on Mars, maybe not far under the surface, maybe 5-10 meters under the surface in an aquifer.
Okay, now let me ask you the big question that the cynics would ask, and that is, well, why go to Mars? To put a pound of anything on Mars is on the neighborhood of about $1 million just to put a pound of anything on Mars. To put a human on Mars is perhaps your weight in diamonds. So what do we get out of it? We don't get weather satellites. We don't get internet reception. What do we get by going to Mars? Can we mine Mars? Is there an economic payoff? That's what I'm asking.
I would, just to be honest, I'd say no. I'd say the Martian exploration is a visionary agenda that's designed to sort of plant our flag, not any country's flag, hopefully the world's flag, on another world and say, we can explore the solar system. And this is how we would make a base of operations, and this is how we would do it. And we could live independent of the Earth. So, the long-term visionary aspect of this is that when an off-Earth colony exists, the first one.
Okay, Professor MP, we have to take a short commercial break, but after the break, we're going to leave Mars and go to the solar system. What about the moons of Jupiter and Saturn? What about the asteroid belt? Can one day we mine the asteroid belt? Welcome back to Science Fantastic with Professor Michio Kaku. Today we're talking about exploring the universe with astronomer Professor Chris Impey of the University of Arizona in Tucson, author of the books How It Began, How It Ends. His latest book is called Beyond Our Future in Space. And also you may want to go to my website, mkaku.org, mkaku.org. It gives you my tour schedule where I'll be signing books on a book tour. My latest book is called The Future of the Mind, How Physics is Beginning to Unravel the Secrets of the Living Brain. Telepathy, telekinesis, recording memories, sending memories. Believe it or not, we can do all of the above complements of modern physics. And the book hit #1 on the New York Times bestseller list 2 years ago, and it's now in paperback form. Once again, the book is called The Future of the Mind. Okay, Chris, let's just jump right into where we left off. We were talking about why we should go into outer space when it's very expensive. I interviewed Carl Sagan before he passed away years ago, and Professor Sagan said that we should go into outer space to become a two-planet species. It's simply too dangerous to put all our marbles on one planet. We need a spare planet. We need an insurance policy because it's dangerous out there. Meteors, comets, ice ages, you name it. The universe is a dangerous place. So what are your thoughts about whether or not we should become at least a two-planet species?
I take his point, and but I would actually put it a little more positively than just hedging our bets against catastrophe. I mean, I think the explorer gene that we have, or our innate curiosity, will lead some of us to move off Earth. It'll never be more than a tiny number of people, so it's not like we can escape anywhere. But that group of voyagers will form the nucleus of a different species, because after some hundreds of generations, that small gene pool will diverge from the root of the evolutionary tree of humans and become a new species, and that will be an amazing experiment, something that we've never done before in our entire history.
Okay, well, we've talked about Mars. Now let's go beyond Mars. First of all, Venus, people say, is a hellhole. It's not a tropical place at all. Very hot on Venus. But what about the outer planets? Jupiter, Saturn. Most people think they're too cold to harbor life. But now we think that perhaps Europa, Enceladus, moons of Saturn and Jupiter may have liquid oceans. So could you elaborate on how is it possible to have liquid water that far out from the sun circulating around Jupiter and Saturn?
Right. It's an important insight from planetary science in the last few decades. I mean, the old idea was the habitable zone, the sort of Goldilocks, not too hot, not too cold place where water can be liquid on the surface of a planet, and the Earth is the only planet that fits that bill. But if you extend the idea of habitability to include subsurface regimes where water can be kept liquid by geological heating from below or by pressure of rock above it, then you actually end up with about 10 or 12 moons in the outer solar system, of moons of Jupiter, Saturn, Uranus, and Neptune, that could have liquid water on them or under them. And if they can have liquid water and they have energy and they have carbon-rich materials, they could have microbial life, any of them.
And this means, therefore, since Jupiter-sized planets are more plentiful, than rocky planets like ours in outer space. This means that perhaps the galaxy could be teeming with moons like Europa that may have some form of aquatic life on them. What are your thoughts about life, therefore, in the galaxy?
Absolutely, and of course, James Cameron made a movie, Avatar, about life on an exomoon, a moon of a planet in another star system. And I think there's an enormous potential for habitability and life on moons of giant planets in what's called the cryogenic biosphere. And the problem for astronomers is we don't know how to detect those worlds. As you know, there are now thousands of exoplanets or planets around other stars, and there are even Earth-like planets around other stars, but nobody, not a single exomoon has ever been detected, because at the moment it's just too hard. So while there's a huge potential for life in those kind of worlds, we don't know how to detect them yet.
Okay, well, speaking about billionaires like Elon Musk, another set of billionaires, this time from Google and Microsoft, about 2-3 years ago, announced an initiative to mine the asteroid belt. Now, some people thought they were lunatics. However, these are reputable billionaires, and they say that there could be all sorts of platinum-based rare metals waiting for exploitation for anyone brave enough to begin the process of mining the asteroid belt. What are your thoughts about that?
Right. On the face of it, it does sound crazy, but it's actually completely doable. And it's not as expensive as some of the things we've been talking about, like setting up a Mars base. It's cheaper than that. Basically, if you had a 500-meter near-Earth asteroid, so an asteroid that does come fairly near to the Earth, you just use the same technologies we've already demonstrated to land on comets, rendezvous with comets, and maybe attach rockets so you can steer the asteroid, and you bring it into an Earth-Moon captured orbit. And then at your leisure, you just start mining it and bringing the minerals down. And a 500-meter sized asteroid has about $2 trillion worth of platinum group metals and probably about the same value of rare earths. That's a lot of money. That's a lot of resources. So clearly it's going to attract some attention from billionaires.
Okay, well, let's take another short commercial break. And after the break, we're going to continue a discussion of, colonizing the universe. What would it take to colonize the solar system and even beyond? With us today is Professor Chris MP, a professor of astronomy at the University of Arizona, author of a number of great books, including How It Began, How It Ends. His latest book is called Beyond, Our Future in Space. Welcome back to Science Fantastic with Professor Michio Kaku. Give us a call. The hotline number is 866-323-2129. Why do we have all the fun? Why don't you have some of the fun by getting to the telephones and calling 866-323-2129. With us once again is Professor Chris MP, professor of astronomy at the University of Arizona in Tucson, author of a new book, Beyond, Our Future in Space. Well, we've talked about Mars. We talked about the asteroid belt and some of the moons of Jupiter and Saturn. Now let's go to the stars. It's a huge jump to make from our little inky-dink solar system all the way to Alpha Centauri, the nearest star system. But, Stephen Hawking and a number of billionaires are now entertaining the idea that perhaps solar cells driven by laser beams can push tiny little parachutes to the stars. The starship would be the size of a postage stamp, so forget about Captain Kirk and the Enterprise. So first of all, what are your thoughts about starships? Is that really just science fiction, or is there any physical basis to going to the stars?
Well, I think, the only way it can happen is this way with a miniaturized situation. So, as you know, the laws of physics are pretty implacable, and if you want to get to a few percent of the speed of light, it takes an enormous energy, unless your payload is really tiny. So they're talking about basically a gram for the payload for the spaceship with a meter-sized solar sail attached to it. And that's, on the edge of doability. They list something like 26 really big technical challenges on their website that they have to overcome to do this project. But I applaud their vision.
And, of course, it's going to take a lot of money. The energy necessary to drive this system is 100 gigawatts of laser power. That's the equivalent of 100 nuclear power plants. Driving this gigantic set of laser beams that has to be aimed very precisely to give these parachute-sized starships a boost. But like you said, hey, it's within the laws of physics, right? Well, speaking about the laws of physics, do you have any other designs for an Enterprise Star Trek-type starships, antimatter engines or nuclear bombs or Orion-type aircraft, spacecraft? What are your thoughts about a starship that could send humans and not postage stamps to the nearby stars? Any thoughts?
Yeah, it's going to take new technologies. I mean, as you know, everything we've talked about so far in the space program is still using chemical energy, and nuclear energy is hundreds of thousands of times more efficient. So we have to go to that kind of propulsion. And there have been designs, like Project Daedalus from 60 years ago. So there are designs, and just the engineering hasn't been done yet. But even so, it's a huge challenge. The amount of fuel needed is high. So I think you have to sort of harvest the fuel as you go along. The best designs I've seen involve taking the very thin amount of hydrogen that's available in interstellar space and using that as your fuel so you don't have to bring it with you.
Well, that's an idea, the ramjet solar engine, but let's take another short commercial break. And after the break, let's talk about starships and maybe even beyond. Let's talk about the Enterprise and warp drive. Is that really a possibility? Once again, you're listening to Science Fantastic with Professor Michio Kaku. Give us a call. The hotline number is 866-323-2129. And our special guest today is all the way in Rome, Professor Chris MP of the University of Arizona at Tucson, author of the book Beyond, Our Future in Space. Welcome back to Science Fantastic with Professor Michio Kaku. In this hour, we're talking to Professor Chris MP of the University of Arizona, author of an exciting new book called Beyond, Our Future in Space. And if you watch the movie Interstellar, realize that the people backing that film were physicists at Caltech and other great universities, using powerful computers to simulate what it would be like to go through a wormhole. And if you watch the end of that movie, they actually wind up on what I do for a living. What I do for a living is I work on something called string theory. String theory talks about wormholes not just in 4 dimensions, but in 11-dimensional hyperspace. And there is Matthew McConaughey at the end of the movie floating in 5-dimensional hyperspace. And they have a bunch of equations that filter on the screen. I look at the equations, and yes, some of the equations were actually correct. They were string equations. But, of course, that's science fiction. String theory is not developed enough to answer the question as to whether or not we can create a wormhole. But we have with us on the line Professor Chris MP, author of the book Beyond, Our Future in Space. So what are your thoughts? It's a long shot, but what are your thoughts that if we really wanted to get to the stars the way they do it in movies like Interstellar and Star Trek, you have to have a wormhole machine. What are your thoughts?
So, yeah, that involves technologies that we don't know how to develop yet. But I would mention something that I think we could do right now that would get us to the stars. It's maybe not as glamorous as a wormhole and warp drive. The technology we need is the technology of suspended animation, which will evolve in natural ways out of just medical science, because people are researching what happens when we die or we nearly die. And there have been experiments to replace body fluids of pigs and dogs, which are human analogs among the mammals. And basically, if we can, take ourselves down into a wait state, which is really in the realm of possibility, then that's how people will get to the stars. Of course, they'd lose all connection to the people they left behind, because they'd just be going into the deep freeze or a wait state and wake up to their new future. But that's something that we think we can do without any new technologies or worrying about the laws of physics.
Now, of course, frogs and certain fish can be frozen solid in a lake during wintertime, and when they thaw out, they're perfectly fine, even though they underwent suspended animation. But that's because they use antifreeze. Frogs and fish will use glucose as an antifreeze to change the freezing point of water, but antifreeze on that level will kill a human being. So what are your thoughts about freezing the body the formation of ice crystals, and the use of antifreeze, which is often lethal to the human body if we try to use antifreeze to change the freezing point of water. So what are your thoughts? Is it a technology that's around the corner, or we still have a few decades more to work on?
I think there's experimentation that's going to get us there. The fluids that people are using with pigs and dogs that take them down essentially into a wait state for days or even weeks and then bring them back mostly successfully involve glycol or some composite that involves glycol. We could also learn some tricks from other creatures, the tardigrade, so-called water bear, these tiny little creatures that are about 1/10 of a millimeter. They've developed the trick of cryptohydrosis, or taking themselves down to 1% of their normal water concentration, and they seem to be able to survive for centuries that way. So, nature has done this with smaller creatures than us, and NASA's studied tardigrades, actually, to see what their trick is. So I think that research is probably going to lead to something interesting.
Okay, and now let's say a few words about what we expect to meet if we meet an advanced civilization in outer space, something straight out of Hollywood. Astrophysicist Nikolai Kardashev of the former Soviet Union had a scale, type 1, type 2, type 3, of advanced civilizations, perhaps thousands of years more advanced than us, based on energy consumption. So could you summarize a little bit about what we might expect to find once we do reach the stars and perhaps make contact with an extraterrestrial civilization that's more advanced than ours?
Right, and in this Kardashev scale, where 1 is controlling your energy of your star, we're not even a 1. We're like a fraction of 1 because we barely use 1 part in a billion of solar energy. So we're barely on the scale. The extreme of his scale, of course, are creatures that control the energy or the resources of an entire galaxy. And my gut tells me that anything that much more advanced than us is essentially going to be unrecognizable. I think, much as I love the science fiction and I read it and I look at the movies and the TV shows, it's incredibly anthropocentric. It's really reflecting us more than anything else. And I think life is going to be pretty strange, especially when it's more advanced. And so I think it may be unrecognizable. I think it's not going to be like us at all.
And then the $64,000 question. How come they don't land on the White House lawn and advertise their existence and say, here we are, folks? What are your thoughts? Everyone has their own ideas about this.
Right. And Fermi, of course, asked this in 1950. Where are they? Making the calculation that there's got to be a lot of life out there, and we're unlikely to be the first intelligent technological species. And I agree with that argument. I think space is big, so one part of the answer may just be that intelligent life is very thinly sprinkled through the galaxy, and we already know how hard it is to visit the stars, so you have to be pretty advanced to even be doing that kind of thing. So that's part of it. And then the other part of it just may be that they're not inclined to be interested in us. Apathy is maybe not a good answer. It's not the kind of thing we want to hear, but we may have nothing to teach someone that's that much more advanced than us, so they may be disinterested in us.
Yeah, I lean toward that in the sense that when you walk in a forest and you see an anthill, do we go down to the ants and say, I bring you trinkets, I bring you beads, I give you nuclear energy, take me to your ant queen, or do we step on a few of them? Well, unfortunately, we have run out of time. Once again, our special guest today is Professor Chris MP, author of the book Beyond, Our Future in Space. Chris, thank you so much for being on Science Fantastic.
Thanks, I've enjoyed it a lot.
Now, Science Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And in this hour, once again, we're going to throw the lines open because this hour is your hour. Okay, well, moving right along, let's take the next listener phone call.
Yeah, listening from Northeast Pennsylvania, WILK, and the sun will interest me the most. How it keeps, where the energy comes from, how it keeps shining, the diameter, and if it shines on the backside also. Thank you very much. Bye-bye.
Okay, well, the sun does not shine on the backside. It shines uniformly throughout the entire sphere, and it does so because of a process called fusion. In other words, hydrogen gas, which is what the sun is basically made out of, is compressed evenly on all sides by gravity, and as it compresses, it heats up in temperature. Just like the opposite of your refrigerator. When you expand the gas inside the coils of your refrigerator, it gets cold. When you compress gas, it gets hot. So that's what happens to the sun. Gravitational pull turns gravitational energy into heat. When you hit several tens of millions of degrees at the center of the star, protons are slammed into protons and hydrogen, creating helium. And so the fusing of hydrogen into helium creates energy via E equals mc squared. So M is a tiny bit of hydrogen which turns into energy. E is energy, and C is the speed of light squared, which is a humongous number. That's why even a tiny bit of uranium will unleash the atomic bomb. So a piece of the sun, no more than a teaspoon, has enough energy in it to devastate all of New York City. That's the power of the sun. Now, if you were to think that the sun shines because of oil or coal, you would have a problem. First of all, there's no air out there, so there's no oxidation of coal or oil to heat up the sun. And second of all, you can also show that even if there was oxygen out there, it would be exhausted in a matter of just a few hundreds or a few thousands of years. And yet the sun has been burning for 4 to 5 billion years. And so a new force is involved, not the force of fire, but the force of nuclear fire. And that force is unleashed by Einstein's E equals mc squared. Okay, well, let's move right along to the next question.
Hi, Dr. Kaku. This is Peter Kleiman. Glad to talk to you again. Once again, I just had a question on physics. My question is, why is the speed of light not something faster or slower? Why is c the value that it is? Is it different in other universes? Is it the same across the whole entire multiverse? Why is it a certain value? Thank you for letting me ask a question. Thanks. Bye.
Well, you ask a question which is quite embarrassing for physicists. The short answer is we don't really know. Einstein simply starts with the speed of light being what it is, and then he probes the consequences of that fact. But then you can run the videotape backwards and say, now, wait a minute. Where did that first assumption come from? Where did the speed of light itself comes from? And the answer is we don't really know. However, in our universe, we think that the speed of light is a constant, just the way Einstein predicted. When we look at radiation, light radiation coming from the distant galaxies at the very edge of the visible universe, we find that the laws of physics and the laws of optics are the same, exactly the same. We don't see any difference at all. So this distant galaxy could be next door, and the radiation that we get from them would be very similar. And so we see no change in the laws of physics in this universe. However, you ask another question, and that is there a multiverse of universes? And in these other universes, can the speed of light be different? And the answer to that is, well, maybe. First of all, I work on something called string theory, which we think is a successor to Einstein's theory of gravity. We think it is the leading candidate for a theory of everything. In fact, if you saw that Oscar-winning movie, The Theory of Everything, the one problem with that movie is they never told you what the name of the theory is. They simply talked about Stephen Hawking's life and his ailment. Well, the theory is called string theory, and that's what I do for a living. And string theory says that our universe is a bubble floating in a much larger arena of hyperspace, in fact, 11-dimensional hyperspace, but there could be other bubbles out there that once in a while bump into our universe. Now, when these universes bump into each other or fission off and peel off a baby universe, the laws of physics can change. And so we have a multiverse of universes such that each universe has its own string theory. In other words, the different constants of nature, including the mass of the electron, the speed of light, things like that, may actually be different. The laws of physics may actually be different in these other universes. Now, can we prove it? Well, the Europeans think we might be able to have a handle on this question. They plan to launch LISA into orbit in the next 20 years. LISA is the Laser Interferometry Space Antenna. It is designed to pick up gravity waves not on the Earth. We've done that just a few months ago, gravity waves on the Earth, but gravity waves in outer space. Gravity waves emitted not from colliding black holes, we did that just a few months ago, but gravity waves from the creation of the universe itself. And that should give us radiation from the pre-Big Bang universe. And then we can have numbers, real measurable numbers, to answer the question, are there different laws of physics in other universes? So the short answer to your question is we don't know, but it is room for experiment, and the European Space Agency will send satellites into outer space to measure gravity waves from the Big Bang, and that should give us a clue as to whether or not other universes can exist. And then, of course, everyone wants to ask the last question, is Elvis Presley still alive in another universe? Well, if the speed of light can change in other universes, then, yeah, there's always a chance that the king could be alive in another universe. Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. Let's take the next listener phone call.
Hi, Professor. This is Tony calling from Jasper, Florida. My question is, if two spaceships are moving toward each other at 186,000 miles per second, the speed of light, what is the total impact of the collision? Is it 186,000 miles per second, or is it double? Thank you.
Well, you ask a question that the young Einstein asked himself when he was 16 years old. You see, if the speed of light is a constant, that means that all sorts of bizarre distortions take place. First of all, if you're coming at an object at near the speed of light, and it's coming at you near the speed of light, then common sense tells you that the relative velocity is twice the speed of light. Or let's say you're in a train that's speeding near the speed of light, and you have a flashlight. You light the flashlight in the direction of motion of the train. Since the train is moving at the speed of light, and the light bulb is emitting light at the speed of light, then an outside observer would say that the light beam is moving at twice the speed of light. Wrong. We've done this experiment. It is always according to Einstein's theory. Velocities do not add. That's the simple question. In fact, there's even a mathematical formula that shows that if you're moving at the speed of light or near the speed of light, and you're moving in a train that's moving near the speed of light, the sum of the two is not twice the speed of light. You have to divide by a certain relativistic factor. Now, how is it possible that an object can seemingly have two different velocities depending upon who measures it? And the answer is that a man inside a rocket ship, his brain slows down relative to somebody looking at the rocket ship. So let's say you have a rocket ship traveling near the speed of light, and you turn on a flashlight. By rights, the flashlight should be going at twice the speed of light, but it isn't. It always moves at the speed of light. Now, you may tear your hair out saying, how's that possible? And the answer struck Einstein in a streetcar in the spring of 1905. He was thinking about the clock tower, the famous clock tower in Bern, Switzerland, as the streetcar was leaving, and he asked himself a question. If this streetcar were moving at the speed of light, what would I see when I looked at the clock tower in Barren. Then he got it. He said that a storm broke in my mind. And that is, the person inside the train, his brain slows down because time itself slows down in the rocket ship. Every time he tries to measure things, it always comes out that the speed of light is exactly the same, no matter if the light beam is moving toward you, the light beam is moving away from you, or the light beam is moving at an angle with respect to you. Now, that violates common sense. Everything in your fiber, everything in your experience tells you that velocities add. Well, wrong. The universe does not believe in your common sense. The universe says, nope, that's not true. The speed of light is a constant no matter how you measure it in any frame. And we've done this. Time and time again, we've sent rockets, ships into space, airships. Each time, the speed of light comes out exactly the way Albert Einstein said. In fact, your GPS system in your cell phone, in your pocket, depends on this. If Einstein were wrong, all GPS systems on the Earth would fail, because time does beat at a different rate for GPS satellites orbiting the planet Earth. And so you say to yourself, well, that violates common sense. The answer to that is tough. Sorry about that. The universe does not obey your common sense. Welcome back to Science Fantastic with Professor Michio Kaku. Once again, the lines are open. Okay, well, let's move right along to the next listener phone call.
Yes, this is Jimmy. Ever since I was a kid and I learned about the men walking on the moon, I wanted to be the first human to walk on Mars. And so as I grew, I took studies that direction, and I learned that we could grow oxygen and that we can grow water. But one of the largest stumbling blocks was the electromagnetic field of Mars was too weak to maintain an atmosphere. And my question is there a way that we can create a stronger electromagnetic field for the planet? Thank you. Bye.
Okay, well, Mars has been in the news ever since NASA said that, yes, we are going to Mars sometime after 2030. But the question is, why is Mars such a barren, bleak place? Well, it has very little atmosphere. Atmospheric pressure is 1% that of the Earth, and it's basically made out of carbon dioxide. But why? Why did Mars lose most of its atmosphere and, as a consequence, lose most of its liquid water? Because once upon a time, there were liquid oceans on the surface of Mars. And the answer you correctly pointed out is that Mars has almost no magnetic field. A magnetic field is very useful because it acts like a shield protecting you against the solar wind. The solar wind is very faint, but it buffets the atmosphere of every planet and blows a lot of the molecules into outer space. So because Mars has almost no magnetic field, it has no protection against the solar wind, which in turn blows the molecules of the atmosphere into outer space, causing Mars to lose 99% of its atmosphere. Now, let's say we terraform Mars. Let's say somehow we're able to raise the temperature of Mars and inject methane and other kinds of greenhouse gases and raise the temperature of Mars. The question is, won't we lose the atmosphere again? Isn't it basically a pointless exercise in futility to try to terraform Mars when the atmosphere is going to be blown off anyway? Well, yes and no. First of all, even if you create an unstable atmosphere of Mars, it's good for a few thousand years. So, in other words, yes, we can create, with tremendous expense, an atmosphere for the planet Mars. It would cost hundreds of billions to trillions of dollars, but it's going to be stable for thousands of years. Then, thousands of years later, you'll probably have to do it again because, of course, the atmosphere, the newly formed atmosphere, will gradually leak out. But there's also another factor involved. If you raise the temperature of Mars sufficiently, it means that the polar ice caps will begin to melt because they're made out of dry ice and ordinary ice. And as the polar ice caps thaw out, it releases more greenhouse gases into the atmosphere, which accelerates the heating of Mars. So we have another effect taking place, a runaway greenhouse effect. The warmer Mars gets, the more the polar ice caps melt, releasing more greenhouse gases into the atmosphere, which raise the temperature even more. So there is room for hope. Even though it may cost upwards of $1 trillion to initiate this process, once it starts, it generates enough heat to sustain it for thousands of years. Welcome back to Science Fantastic with Professor Michio Kaku. Once again, the lines are open. Moving right along now, let's take the next listener phone call.
Hi, my name is Solomon. I'm calling from Wilkes-Barre, Pennsylvania. 103.1 FM is the station I'm tuned to. My question to Professor Michio Kaku is that in most explanation of gravity and most depiction of what gravity look like, they show us a fabric and whatever objects that are pushing down on it, causing gravity. My question is, if there is no up or down in space, how does gravity indent space-time like a fabric? It just doesn't make sense to me. If you could please explain that.
Okay, well, you ask a question that a lot of people are asking, and that is, we have this picture that space-time can be viewed as a fabric like a trampoline net. So think of a trampoline net, and then drop a bowling ball in the middle of the trampoline net, and the bowling ball, of course, sinks. Then you take a marble, you shoot a marble along the trampoline net, and lo and behold, my God, it orbits. It goes in a circle. The marble goes in a circle around the bowling ball. Why? Because the fabric of the trampoline net is bent. Now, this is an explanation of how gravity then warps the space-time around the Earth, and that's why the Earth goes around the sun. That's why you are sitting in your chair right now. Why are you sitting in your chair? Most people would say you're sitting in your chair because gravity is pulling you down. But Einstein says, nope. That's not why you're sitting in your chair. You're sitting in your chair because the Earth is warping the space-time around your head, and it is pushing your head into your chair. In other words, gravity is a push and not a pull. There is nothing pulling you down like gravity toward the center of the Earth. Space is pushing you down into the Earth. Now, what this questioner asks is the analogy. Isn't the analogy wrong? Because the analogy itself requires gravity. Gravity pulls the bowling ball down into the trampoline net. So, aha, it's circular. I got him. I showed that Einstein's theory is wrong because it uses gravity to explain gravity. Well, just remember that it's only an analogy. Perhaps a better analogy would be as follows. It was Shakespeare who once said that all the world is a stage, and we are like actors and actresses making our entrances and exits on the stage of life. Well, now imagine that the stage, this empty arena called space-time, is warped. And as you walk across the stage, it is impossible to walk in a straight line because of the warping of the stage. Or take a sheet of paper. Crumple the sheet of paper and put an ant on the sheet of paper and ask the ant to move in a straight line. The ant cannot. It's buffeted to the left, buffeted to the right. Now put the sheet of paper in outer space. Now there's no gravity. There's no gravity. And then you ask the ant, can he move in a straight line? And the ant would still say, no. I try to walk in a straight line, but every time I try, I hit a fold, and I go to the left, I'll go to the right. So in other words, the thought experiment of Einstein is correct. The curvature of space gives you the illusion of a force. But the analogy of the bowling ball, the analogy of the trampoline net, uses gravity, and so it is slightly defective. A better analogy would be to put the sheet of paper into outer space and put an N on that sheet of paper, and then you are not referring to gravity at all to explain gravity. Michio Kaku. Yes, this is your opportunity to share your thoughts on national radio. Okay, moving right along, let's take the next listener phone call.
Hi, Dr. Kaku. This is Alan from Denver, Colorado, and I had a question about life on Europa or any moon surrounding Jupiter. The question is, would Jupiter's magnetic field shield the moons from solar radiation? Because as we know, on Earth, we need our magnetic field or life couldn't exist. Would that same shield exist for the moons of Jupiter? Thank you.
Well, it turns out that our space probes, as they approach Jupiter, sometimes they're overwhelmed by this barrage of radiation. Jupiter is quite radioactive. And in fact, when you turn on your TV set and you see that snow when you're between channels, especially with the older TV sets, where does that snow come from? Believe it or not, much of it comes from Jupiter. That's right, Jupiter is a gigantic creator of electromagnetic disturbances, and it also has a magnetic field. Now, as you correctly pointed out, a magnetic field can protect you against the solar wind. Think of Mars. Why is Mars a frozen desert? Mars is a frozen desert because it's lost most of its atmosphere due to the solar wind. Because Mars has no magnetic field to speak of, it has no shield to protect itself against the harsh ionizing wind that comes from the sun and blows the remaining atmosphere of Mars into outer space. So the question is now, Jupiter has satellites going around it like Europa. We think that Europa has a liquid ocean underneath the ice core. How do we know? Because of tidal forces. Tidal forces are enough to generate heat, volcanic heat, at the center of Europa, hot enough to melt the ice cover of Europa, creating an ocean. In fact, we've estimated the size of that ocean, and it's actually in volume larger than the oceans of the Earth. And the Earth, of course, is much bigger than tiny Europa. And so then the questioner asks, the comment, the solar wind, is it deflected by the magnetic field surrounding Jupiter? Well, I think what the questioner is getting at is any life form on Europa protected from the solar radiation? And to some degree, yes. To some degree, Jupiter's magnetic field acts as a shield protecting Europa. However, Jupiter itself has a tremendous spray of radiation emanating from it, and so I don't think it's much of a consolation prize. In other words, any life form on Europa will have to live underneath the ice cover because the radiation from Jupiter is quite intense. So yes, Jupiter does deflect some of the solar radiation coming from the sun, dampening the radiation that would hit a moon of Jupiter. But that doesn't mean that life forms on Europa are let off the hook, because Jupiter itself generates a tremendous amount of radiation. Okay, well, let's move right along to the next listener phone call.
So my name is Tom. I'm calling from St. Petersburg, Florida, on 8:20 a.m. news. My question is regarding the phenomenal Philadelphia experiment. We've seen the documentaries. I've seen the documentaries, quite impressive. And we've seen the movies, part 1 and 2. The government officially denies the existence of time travel, but some scientific factors prove otherwise. Now, what exactly happened with the Philadelphia experiment back in 1942, 1943? So they tried to hide shit from the enemy, and they happened to get really well hidden and disappearing. Thank you.
Well, you ask a question that I often get on email, and that is, what about the Philadelphia experiment? As you correctly pointed out, it's a Hollywood movie, a movie in which scientists from World War II experiment with electromagnetic radiation on a battleship and accidentally sent the battleship backwards in time. Well, let's go back to the origin of the story. It goes back to the year 1955. In the year 1955, Albert Einstein died. And it was in all the papers that he could not finish his fabulous unified field theory, the theory of everything. A theory, by the way, which I work on professionally. Well, because of that, many people speculated what could possibly have been in that unfinished theory of 1955. Then an astronomer and also a writer on UFOs receives a letter in the mail stating that, yes, he was in the Navy, and yes, Einstein completed his unfinished work. It was a misnomer in the press. He actually completed the work, and the work talked about gateways and time machines and so on and so forth, and the person says that he witnessed things disappearing because of Einstein's unified field theory. Well, that person has never been tracked down. Most people think it was, in fact, a hoax. This entire story based on one letter referring to Einstein's unified field theory. First of all, I work on Einstein's unified field theory. That's what I do for a living. We even have a better version of it called string theory, which we think is the fabulous theory of everything. Does it allow for wormholes? Yes, it does allow for gateways into perhaps other universes, perhaps gateways into the past. But there's a catch. There's always a catch someplace. And that is, you can also calculate the energy necessary to create a gateway through space and time. And it is fabulous. It is the Planck energy. It's a quadrillion times the energy of our largest machine, the Large Hadron Collider based outside Geneva, Switzerland. In other words, the letter was a hoax. It was a clever hoax because it tried to piggyback over all the press coverage given to Einstein's unfinished unified field theory. So yes, we think we can finish that theory. Yes, it does allow for wormholes, but the energy necessary to open gateways through time is way beyond anything that could have been assembled in 1943, which is when the experiment supposedly took place, or even hundreds of years into the future. Okay, well, that's it for Science Fantastic. Join us every week when we discuss the cutting edge of science on Science Fantastic.